difficult questions prepared for the panelists, so don't be nervous. But first, we will have a presentation about the carbon footprint of feed. And this presentation is given by someone who has a Master of Science degree in Environmental Sciences. He used to work as an LCA consultant for quite some years before we were able to convince him to work for Friesland Campina and join our team. We had worked with him a lot in the past as well, so we were very happy that he was joining. He is a fanatic chess player, and that also reflects his work because he's always thinking 2 steps ahead. And he's also not afraid to make a critical statement when needed, especially when we work on the sustainability and decision making, like you just heard with the global GWP star answer, for example. He's a true data wizard and very passionate about sustainability. And of course, he is also a co-author on our paper. May I invite Lody Kuling to the stage to tell us about the feed.
Thanks. Yeah, I was talking about challenges in determining footprints over time, not just feed, but footprints over time in general. I will focus on feed in a bit, but also on some other topics. So I will discuss why, what are we talking about when we talk about footprints over time? Why is it important for this specific study? What did we actually do? Go into depth there, especially with regard to the feed ingredients. Give some conclusions from our study, and also provide some guidance on what we can learn from this, from monitoring greenhouse gases in general, and especially at Friesland Campina. So what are we talking about exactly? This figure is probably not new. You've seen it before. It's the breakdown of the carbon footprint of raw milk over the years. This is the part that I'm going to talk about, the purchased resources and to a lesser extent energy. And we see a large decline in the emissions from purchased resources and energy. And they are only limited due to the fact that we use less of them. The most of the reduction is due to other factors. So why is this important? The trends in these background systems, so what happened in the suppliers of our dairy farmers, they have to be taken into account if you want to do a good footprint study over time. And if we do that, on this graph you see a blue line, which is the carbon footprint, including the trends in background systems, which are the main results that we've seen over the previous presentation. And the orange line is if we would neglect all these trends in the background systems. So we would neglect that the electricity system has changed, that the fertilizer production system has changed, that the feed production system has changed. And if we neglect that, then the reduction over time would be 150 grams lower, which would account, this is the figure that you know, that we have a 35% reduction between 1919 and 2019. If we would neglect these background system changes, it would only be 27%. Meaning that on about 1/4 of the reduction that has taken place over the last 30 years is due to the background system. So not due to the activities that our farmers did, but to the activities the suppliers of our farmers did. So that's why it's important to this. What do we do? Of course, you can apply this thinking of what is the trend in the background system to almost everything that enters the dairy farm, from the plastics that they use to the coffee cups. We didn't do that. We focused on the things that are the most important background systems, which are electricity, artificial fertilizer, and purchased feed materials. And in the graph, you see the contribution of the background system changes to this 150 grams reduction. And the electricity system changed in such a way that it only contributed 10 grams of CO2 additional reduction due to the changes. Artificial fertilizer was the majority, with 90 grams of CO2 reduction due to the change in that system. And for the feed materials, it was about 50 grams of CO2. I will zoom in on all of them a bit now, and then focus more on the feed materials. So in electricity production, we modeled based on CBS data what the carbon footprint of electricity was in the Netherlands, because we're talking about the Dutch dairy system here. And the graph shows what the carbon footprint for 1 kilowatt hour of electricity was between 1990 and 2019. And what is striking is that in the first period, there's very little decline, but only since 2000, well, let's say 2015 onwards, there's a large decrease in the carbon footprint of electricity, which is due to the fact that then we started phasing out coal-fired power stations, and also the green electricity production ramped up significantly. For artificial fertilizers, we modeled two things: the changes in the types of fertilizers that were used over time, but also the carbon footprint of the production of these fertilizers. So in the graph here, you can see the blue line, which represents the kilogram CO2 equivalent per kilogram of nitrogen fertilizer produced within the EU. And the drop is significant. So it goes from approximately 8.5 kilograms of CO2 to produce 1 kilogram of nitrogen fertilizer to approximately 3 nowadays. And this is due to mainly due to legislation on a European level about how to deal with nitrous oxide gas coming from fertilizer production, and that has to be avoided. And finally, we model trends in the purchased feed materials. Feed materials are can change in composition over time. So which feed materials do we actually feed our cows? The carbon footprint of this production can change. So we become more efficient, just as we become more efficient in dairy farming. We can also become more efficient in how we grow wheat. And there are changes in the sourcing area. So where do we get these products from? And that can also affect the carbon footprint of this feed material that we purchase as a dairy sector. So we didn't do this alone, because this is a lot of work, and it is also very complex and also out of our own comfort zone in some cases. So for the change in composition, for which data is typically very difficult to obtain due to the fact that for feed companies this is sort of their unique selling point, where they get what the composition of their feed is, and where they get it as well. But so we partnered up with Schothorst Feed Research, who have who do modeling of what kind of feed materials are available in the Netherlands, what are most profitable to put in your feed, what's the quality of the different feed materials in the Netherlands, and with that they do it yearly or twice a year. They model what would be the optimal feed for all kinds of animal groups, including dairy. So we use their data to get a feeling for what is the composition and how it has that changed over time between 1990 and now. Then we also need to wanted to see the trends in the carbon footprint of the production of the feeds. So how were these feeds produced? What were trends in nitrogen use efficiency on the farms all over the world? And for that, we partnered up with Blonk Sustainability, as they call it nowadays, I think. So we asked them to help us model a lot of feed materials that were actually in this mix of feeds that we found in collaboration with Schothorst. And finally, we wanted to know where these materials came from. So they can come from different areas. You can grow wheat in the Netherlands, but you can also do that in France, and you can also do that across the globe in, for example, the US. So based on a tool developed by Blonk, and which is based on data from the FAO, we developed a good overview, a good understanding of where all these feed materials came from over these years. In the rest of this presentation, I won't go into all of this because I think it will take a bit too much time. I will mainly focus on the carbon footprint of the production of feed materials to show what are the things that you should think about when you model these production systems over time. So first I will go into how did we model the cultivation of these feed materials. which trends have we included into this in this modeling, and I'll show some results of all the feed materials of not all, but the main feed materials that we modeled, and try to explain some causes and drivers of the changes that we see in these trends of the feed materials. So, how to model the cultivation of feed materials? Please don't try to read this whole thing. This is what a life cycle inventory looks like. It is based on a blueprint of a dataset from Agri-Footprint database from 2015. But what you can basically dissect this whole table into 4 parts, which are outputs. So what comes out of the agricultural system. You can distinguish the inputs from nature. So how much water did we use to grow these crops? How much land do we use to make these crops? And inputs from the technosphere. So everything we put in that comes from we made as humans. So that's electricity, fertilizer, manure, pesticides, fuels, you name it. And then there's what comes out of the farm. That is not what you actually wanted to get out of it, so the outputs, but these are the emissions. And these emissions can be either to the air, so it can be carbon, CO2 emissions, methane emissions, but it can also be emissions to water, nitrogen emissions, or heavy metal emissions. And the final compartment that emissions can go to is to the soil. We didn't model for all of these compartments, for all of these things, the trends. We focused on the things that have a high contribution towards the carbon footprint, because that's the focus of this study. So we modeled for all the feed materials how the yield changed over time, but also how the inputs changed over time. And for carbon footprint, especially important, the inputs from nature is the land use change. So how much deforestation took place in which countries where certain feed materials were grown for that specific crop. With regards to the inputs from the technosphere, we modeled trends in electricity and diesel, both how much is used as well as what's the carbon footprint of production of these goods. And the same also for pesticides and fertilizers. So for the fertilizers, I already showed you what we found for Europe, but we also looked at other places. And for manure, finally, we modeled just the amount of manure that's used or that's available in the different countries. And from all these inputs and all these outputs, we can then calculate what the emissions, how they would change over time. So they are also accounted, and especially the nitrous oxide emissions and the carbon dioxide emissions, because they contribute to the carbon footprint of these feed materials. So some results after all this. Here you see on the y-axis the carbon footprint of a feed ingredient in kilogram CO2 equivalent per kilogram of dry matter. So it's not a as-is product, but as if it would be 100% dry matter. And you see that for a lot of different ingredients. And then we have a coloring scheme where the most lightest bar on the left is the 1919 data set, and the most dark on the right, which is dark blue, is for 2019, so the end of the trend. And there are a lot of different things you could get from this graph, but I will zoom in on a few of them. And please note that these are excluding land use change for now. I'll come back to that in a bit. So first, let's focus on the grains. So we see that barley, maize, rye, wheat, they're all in there. And they also show a steady decline, which is positive, and is mainly due to the fact that there is a lot of nitrogen use efficiency has increased a lot over time. We also see grains that have been processed further or are byproducts from other streams. For that, we see a similar trend, which is sometimes accelerated and sometimes not, which is due to the energy mix that or the amount of energy that's needed to process them further into that specific product. We also see some feed materials that hardly show any trend. For example, the beet pulp and the citrus pulp. These are feed materials that are residual products from other production chains, and their footprint is mainly, these are very wet products, and their footprint mainly consists of the transport that takes from where they are produced to the dairy farm. So they are very wet products, so then transport is much more important. So these are rather flat, so the only thing we see is that the background systems have become a bit more, energy systems have become a bit more efficient. And finally, there's also an exception where the footprint actually went up over time, which is for palm kernel expeller, also a very important feed ingredient in the compound feed. And that is due to the fact that there was just too little. So we had the supply of 1919 would be way too little to provide what we need nowadays. And that meant that sourcing areas have changed a lot. So where it mainly came from Malaysia in 1990, nowadays almost exclusively it comes from Indonesia, where production is still much less efficient, or carbon efficient, I should say. What we can add to this is what happens with regard to land use change. And there we see the same graph as before, but then stacked on the bars that we just discussed. We see the orange or red bars, and they are not on all of them you can see them. So there are feed ingredients for which land use change is not a problem, but there are also ones there where it is a very big topic, and I will go through them. So for soybean, we all know that deforestation for soybeans is a global problem, especially in South America. This is in Brazil. This is a huge topic, and we see that although we modeled this over time, and also the deforestation over time, that the amount of land use change that takes place for 1 kilogram of soy has remained rather stable. So it's not that we increase or decrease the rate of expanding our area of worldwide area of production for soybean. For other ingredients, we see a different picture. So here I want to highlight peas and rapeseed, for which deforestation or land use change emissions were very important in the early years. So up until 2000 to approximately, they had a big contribution. And afterwards they didn't. And how it come is that? So these deforestation emissions actually come from France. So up until then, France had land use change still attributed, and nowadays, just as in the Netherlands, there is no longer deforestation taking place in France. And finally, we also see some products for which only recently land use change has become a problem, especially for the maize related products. And that is due to, again, new sourcing areas. Maize is recently also been grown in large quantities in the Ukraine, for which also land clearance has taken place. Some conclusions from our study. So modeling these changes in background systems for life cycle assessment or carbon footprint studies, as we've done now, is relevant. It can add a lot of depth to your results. It can add a lot of information, and it can make up to 1/4 of the carbon footprint reduction of raw milk that we've seen over between 1990 and 2009. But on the other hand, it is also very time consuming. I think you can imagine of the amount of work that you have to do to model these things over time for just the raw milk sector. And then you have to multiply that with a lot, because you're going to do that for all kinds of other sectors as well. So you do that for all the feed producing sectors that we've just discussed. And so that's a lot of work, but it's also a unique feature of the study that we did. So it is, as Pablo already mentioned, one of the longest time series, or the longest time series in dairy, and one of the longest time series out there. And it's also one of the first scientific publications that takes this background system changes over time into account. So in that sense, it is also a valuable contribution to the development of life cycle assessment methods. And as I've already stated, 150 grams of reduction coming from your background system is a lot. So it is a large contribution that comes from this area. What can we learn from this? So it's not just about this study, but it's also about after this. I think, and I'm just focusing on Friesland Campina, what we can learn from these insights is that as a cooperative, we need to engage with suppliers in the feed and fertilizer chain at the least, because we know what they can attribute to the reduction that we as a dairy company want to make. And we have to make sure that the reduction efforts, if they take them, are actually visible in the results that we calculate, so that they will be expressed in the kringloopwijzer or the ANCA tool, as mentioned before. On the corporate level, I think it is important that we make sure that we have access to primary carbon footprint data from all our suppliers. So this is an example where it has a large impact for feed, for raw milk, but as a company we buy a lot of things from a lot of suppliers, which all have these same, or not same, but that also have their own development path towards hopefully carbon neutral in the not so distant future. And then from gathering that information, we have to make sure that the reductions they realize are also expressed in our scope 3 emissions, and that we can then put them forth in our goals, for example, with regard to SBTi. And finally, valorization to all the salespeople here. Convince our customers that this story also applies to them. So if they want to reduce their carbon footprint, think about all the supermarkets or all the big further producers of dairy products in their products. They also need the reductions that not just the feed and the fertilizer production, but also that our dairy farmers did. So it is a chain mechanism. Everybody needs to improve. Everybody needs to share that data. And we all need each other to achieve our carbon footprint goals. And yeah, that was it from my side.
Okay, so the last presentation of today will be a little bit more dynamic because we have